Hello, statistics students. We've been working on the field of descriptive statistics, where we're summarizing, analyzing, and displaying data. Now we're going to start merging into the field of inferential statistics, where we're going to use statistics to make inferences about a population. And inferential statistics is all based on probability. So we need to start with learning some probability. So here in section 3.1, we have basic concepts of probability and counting. And there are some terms we need to know. These are defined in your book. I just want to give you an example. A probability experiment is anything we're going to do to generate data. Like, let's say we're going to roll a die. Outcomes are all the possible results of that experiment. And if we're going to roll a die, we can get a 1, a 2, a 3, a 4, a 5, or a 6. Each of those is an outcome. The set of all possible outcomes is called the sample space. And an event is some subset of this sample space, or some collection of outcomes, one or more outcomes. For instance, an event might be rolling an even number, and that's 3 outcomes, a 2, a 4, or a 6. Or rolling a prime number, a 2, a 3, or a 5. Ooh, and if you thought 1 was a prime number, we're gonna have to talk about that. So we have the fundamental counting principle, which is defined on page 132 of our current text, which says if one event can happen this many ways, and another event can happen this many ways, the number of ways they can happen in sequence is this times this. And I'll show you what that means with some license plate problems. So let's say that we're old school California, where your license plate was a letter, number, number. And let's say that you can use any number from 0 through 9 and any letter except O, because O might be confused with 0. So that means we have 25 letters and 10 numbers we could choose from in this letter, number sequence. By the way, note this slide is in school colors, because I have Spirit. Yes, I do. I have Spirit. How about you? So let's say we can reuse all the letters and the numbers. That means you have 25 letters you could choose for the first one. For each one of those, you have 25 letters you could choose for the second one, and 25 for the third, and then the 10 numbers. So according to the fundamental counting principle, the way this can occur in sequence, you just multiply the numbers together, and there are over 15 million license plates if you do it that way. What if you can't reuse any of the letters or the numbers? Well, there are 25 letters you could choose for the first space, but only 24 left for the second. And after you've chosen those two, there are only 23 left for the third. And then, of course, 10 numbers, then 9 numbers, then 8 numbers. If you go with not able to reuse any letters or numbers, now we've gone from 15.5 million to 9.9 million. No es muy bueno. And let's say we can reuse the letters, but not the numbers. Well, that's 25 letters each time, but still the 10, the 9, the 8. And that bumps us up to a little over 11 million license plates. You can imagine the letter, number wasn't going to last long in a state of 40 million people. So we've had to add a 7th character to our license plates. This is called a tree diagram. And it says, if I flip a coin, how many possible outcomes are there? So I'm going to break it up into first flip, second flip, and third flip. My first flip, I have two choices of outcomes, heads and tails. If I get heads, the second flip, I could get heads or tails. It doesn't matter what the first flip is, because if the first flip is tails, I can get heads or tails for the second one. And then for each of these, if I have heads first and heads second, I still have two choices for the third flip. And if it's heads first, tails second, I still get two choices for the third flip, or two outcomes. So here is my sample space. My sample space is the collection of all possible outcomes. I'm just going to read them off. Heads, heads, heads. Heads, heads, tails. Heads, tails, heads. Heads, tails, tails. And this is how you identify the entire collection of possible outcomes, is with the sample space. In this problem, we created the sample space by looking at a tree diagram. We generated the sample space by looking at the results of our tree diagram. And notice it ends with tails, tails, tails. That's our last one. So the question is, how does the fundamental counting principle relate to the tree diagram and its resulting sample space? Well, if I have two choices for the first flip, two choices for the second, and two choices for the third, that must mean there are 2 times 2 times 2, or 8 outcomes in the sample space. 1, 2, 3, 4, 5, 6, 7, 8. So that's how you can check your sample space, by using the fundamental counting principle. Now let's say that I have 3 pairs of pants and 5 shirts. Assuming they all go together, how many different outfits do I have? Well, 3 pants, 5 shirts, 3 times 5. The fundamental counting principle says I have 15 possible outfits. Let's identify them. I'm just going to call my pants number 1, 2, and 3, because I have 3 pants. And my shirts will be shirt 1 through shirt 5. So for pants number 1, I have shirt 1 through shirt 5. Pants number 2, shirt 1 through shirt 5. Pants number 3, shirt 1 through shirt 5. And you can certainly see that we do have 3 times 5, or 15 possible outcomes. Now, there are 2 vocabulary terms here. One is theoretical probability, and the other is empirical probability. Theoretical probability is mathematical. Empirical probability is experimental. So theoretical probability says the probability of getting some event E happening is you find how many outcomes are in E divided by the total number of outcomes in the sample space. For instance, let's say E is rolling an even number on a die. Well, how many outcomes are there in E? Well, you can roll a 2, 4, or 6. That's 3. There are 6 items in the sample space. So the probability of getting an even number would be 3 out of 6. But let's say my problem was not quite that easy. Then maybe I need to do some experiments and come up with experimental probability. So maybe I'd roll a die a whole bunch of times. I'd see how many times event E occurs, or in this case, how many even numbers I roll, out of the total number of trials. And it turns out that this is really, really cool in gambling. So I'm going to stop sharing this screen. I'm going to pause recording for a moment, and I'm going to load up some screenshots I did of some slot machine gambling. I'm back. Alrighty, so this is called 100 play draw poker. You're dealt 5 cards, and you can keep however many cards you want, and you keep the same cards on 100 hands. So as it turns out, this is actually an experiment and I'm running it 100 times. I'm running the experiment 100 times at once. So I'm keeping this pair of aces, and I'm trying to figure out the probability of getting 3 of a kind. Now, mathematically, that can get a little complicated, because I can say, well, what's the probability if I keep these 2 cards, what's the probability that I get another ace? Well, the problem is if I get another ace, that's included if I get 2 aces. So I have to subtract out first off, I have to figure out the probability of getting at least 1 more ace. Then I have to subtract out the probability of getting 2 aces instead of just 1. And then maybe I have to subtract out, well, I also definitely have to subtract out the probability of getting like an ace and then another pair over here, because that wouldn't count as 3 of a kind, that would count as a full house. So running this, calculating this mathematically, the probability of getting 3 of a kind if you hold a pair is a little bit difficult. So let's just run some experiments and see what we get. Maybe you can keep track of these for me. So I held the 2 aces here, and then I drew, and I ended up with 8 3 of a kinds. You can see here, I just got the aces, that's jacks or better, and that happened 75 times. One time I actually did get a full house. Another time, or 13 times, I got 2 pairs. Twice I ended up with 4 of a kind, so I got 2 aces twice. But I'm only interested in 3 of a kind, so keep track of this for me. So 8 out of 100 here, I got 3 of a kind. Now in this one, I decided that I was dealt 4 clubs. I want to get a flush. Now getting a flush is easy. Running the calculations for getting a flush is pretty easy. There are, let's see this, 13, 12, 11, 10, 9. There are 8 spades left in the deck. There are 9 spades left in the deck, and there are 47 cards left in the deck. So 9 out of 47, 19%. There's a 19% mathematical chance that I'll get a flush here. Let's see what happened in reality. So let's do the experimental probability. The theoretical probability is 19%. This time my experimental was only 17. So keep track of that for me too. If I held 4 of one suit, the experimental probability was 17 out of 100 because I did 100 hands. Here's one where I held another pair. And this time for 3 of a kind, I only got 11. So now it had whatever I had last time plus 11 out of 200. Here I held a pair. This time I got 10, so now it's add 10 more and it's out of 300. Here I held a pair. This time I got 13 3 of a kind experimentally. So now add that 13 in the numerator, now it's out of 400 tries, 400 trials. Here's another one where I held 4 of one suit. So we're gonna add this to that other one that was called a flush. And this time, got 14 flushes experimentally. Here I held 2 pair. What's the probability that I'll get a full house? Well, a full house is 3 of one card and 2 of another. So I need either a 4 or a 7 here. And there are 1, 2, 3, there are 4 cards I could get. I can get one of the two remaining 4s or one of the two remaining 7s. So that's 4 cards, and there are 47 cards left in the deck. So 4 out of 47 is 8.5%. So I expect 8 or 9 full houses out of this 100. And I got 13. Not bad. And that's it for my trials. So I hope you understand now the difference between mathematical or theoretical probability and experimental probability. So all of these playing with the cards, that was experimental probability. When I actually ran the calculations to determine how many cards are left out of how many, that's mathematical. No, I'm sorry, that's empirical, that's experimental. All right, continuing on. One of my favorite quotes in all of statistics: without data, all you have is an opinion. So there's a rule called the law of large numbers. The law of large numbers. And what the law of large numbers says is that the more trials you run, the more experiments you do, the closer your experimental probability is going to be to the theoretical. So I'd like to show you this chart. Now this was done This comes from my old textbook. This was flipping a coin, and we're recording, the proportion of heads. So on one flip, we obviously got heads. So the probability, the experimental probability was 1 or 100%. Now we know the probability of flipping heads is 50%. Okay. On the second flip, well, I'll be darned, on the second flip, we must have got tails. So now we're down to 1 head, 1 tail, we're at 50%. On the third flip, we must have gotten tails again, because we're now down here at one out of 3. On the fourth flip, we got heads, so now we're up at 50% again, and this bar is the 50% line. Then on the fifth flip, we must have got heads, because now we're at 3 out of 5, or 60%. Which would be right here. And then on the, looks like the sixth flip, we got heads again, because now we're at 4 out of 6, or 66%. Anyway, this was done a whole bunch of times. You see, for a while, we were above 50%. And then it kind of went low for a while. We had a bad run. We got a bunch of tails. Sometimes that just happens. That doesn't mean anybody's cheating. That just means it happens in probability. But you'll notice over the long run, slowly we started creeping back up to 50%. The coin doesn't know that it's supposed to be 50% heads and 50% tails, but there's just kind of a law of the universe that says that you keep doing this enough times, you're going to get close to 50%. Now, casino games, the probability is against you every time. So how do people win? Well, they get a lucky winning streak and they're up above 50% for a while. That's when it's really smart to quit. Because if you keep doing it for a while, you're going to go back to what the probability is. And in gambling, in a casino, the probability that you win is always less than 50%. There's the range of probabilities rule. And what it says is that the probability of any event E has to be between 0 and 1 inclusive. You can have a probability of 0, you know, what's the probability that the sun will rise in the west tomorrow? It's 0. What's a probability of 1? Probability of 1 is, you know, not really 1, but okay, if you roll a die, you're going to roll a whole number. That's a probability of 1. Now you might say, well, what if the die sits on the edge? Yeah, have you ever seen that happen? Me either. So 0, 1. What's the probability that you roll a 3.5? 0. And, you know, of course, all other probabilities have to be between those two extremes or equal to them. Another vocabulary term is a complement. Not compliment with an I. Compliment is what you pay me for looking pretty. Oh, Mr. Miller, you look nice today. Why, thank you for the compliment. That's not this. This is a complement, and a complement means kind of the opposite of. So if you have an event E, the complement is not E. So if my event E is rolling an even number, E prime, as we call it, is a complement, and that would be not rolling an even number, or we might say rolling an odd number. So what if you take all of the outcomes in event E and add to that all of the outcomes in event E prime, which is the complement? What should you end up with? What you should end up with is the entire sample space. So if the E is rolling an even number and E prime is rolling an odd number, well, here you should get 2, 4, and 6. Here you should get 1, 3, and 5. And that is certainly the entire sample space for rolling a die. And the probability of event E plus the probability of everything except event E has got to be 1 because there's no other choice. Now, there's a type of problem called the birthday problem, and perhaps you've heard of this before. And that is, how many people do you need to have in a room before there is a 50% chance that 2 of them have the same birthday? You might say, well, that would have to be like 182 or something, and it's not. Turns out I can never remember this number. I think it's like 23. You might say, how can it be 23? Well, I'm going to show you now, if I can remember how to share my screen. So it's difficult to figure out probability of people having the same birthday, but it's really easy to figure out the probability of people not having the same birthday. So we're going to use the complement here. So if you think of it, the probability that 2 people have the same birthday plus the probability that 2 people don't have the same birthday has got to be 1. So the probability that at least 2 people have the same birthday is 1 minus the probability that nobody has the same birthday. Think of that. The probability that 2 or more people have the same birthday is 1 minus the probability that nobody has the same birthday. So how do we figure out the probability that nobody has the same birthday? Well, the first person, there are 360, we'll just assume a 365-day year here. There are 365 dates that person could be born on out of the total of 365. Now, what's the probability that the second person would not have the same birthday? Well, you got 364 days left to choose from out of 365. And then if these 2 people do not have the same birthday, well, there are 363 left for the third person, so as not to have the same as either of these 2 out of 365. You keep multiplying these together until the probability gets to 50% or very close to it. It won't be exact. Well, I just said this is the probability that two people do not have the same birthday. So 1 minus that must be the probability that at least two people do. So if you run this calculation and keep doing it until you come up with a probability, 1 minus all of this is equal to at least 50%. And then you count how many of these fractions there are. I believe the answer is 23. You'd think I'd have looked that up before I started preparing this video, but I did not. So that's it for the fundamental counting principles and basic probability. Have a great day.